Welcome! Today we are diving into the chemistry world of solutions, where different substances mix uniformly. We'll build intuitive visuals and walk through key expressions and colligative properties. A solution is a homogeneous mixture where a solute dissolves in a solvent. There are many types depending on the phases involved: solid and liquid, gas and liquid, liquid, and so on. We express how much solute is present using concentration measures. Mass percent shows grams solute per 100 grams solution. Molarity counts moles of solute per liter of solution. Molality counts moles of solute per kilogram of solvent. Mole fraction looks at the ratio of moles of one component to the total moles. Now consider gases dissolving in liquids. Gas solubility decreases with temperature and increases with pressure, which is why carbon dioxide fizzles out faster in warm soda. We can picture the gas molecules above the liquid and how they scatter less when pressure increases. Solid solutions have atoms of the solute occupying lattice positions in the solid solvent. Think of alloys like brass, where copper and zinc atoms mix in the solid crystal to change properties. Colligative properties depend only on the number of solute particles, not their identity. We'll explore relative lowering of vapor pressure, Raoult's law, elevation of boiling point, depression of freezing point, and osmotic pressure. First, vapor pressure lowers because solvent molecules are fewer at the surface. Relative lowering equals the mole fraction of the solute. Raoult's law says the vapor pressure above a solution equals the mole fraction of the solvent times the vapor pressure of the pure solvent. Adding solute pushes the boiling point higher and the freezing point lower. Elevation of boiling point uses the equation delta T sub B equals K sub B times molality times Van Hoff factor. Depression of freezing point uses delta T sub F equals K sub F times molality times Van Hoff factor, showing that the magnitude of temperature change depends on how many particles the solute splits into. Osmotic pressure is the pressure needed to stop solvent flow across a semi-permeable membrane. The formula pi equals molarity times the universal gas constant times temperature. This property is often used to determine molar mass by measuring how much pressure the solution exerts. We can use colligative properties to find molecular mass. For example, if a known mass of solute causes a known delta boiling point, we use delta T equals K sub B times molality to solve for moles, then divide the mass by moles to get molar mass. Sometimes measured molar masses differ due to ionization or association. The Van Hoff factor, I, tells us how many particles form from one formula unit. When a salt like sodium chloride dissolves, it forms two ions, so I is about 2. Abnormal molecular mass is the boot camp clue that our I value is not what we expected. We covered solutions, concentration expressions, solubility trends, colligative properties, and how these ideas help determine molecular mass. Keep visualizing how particles interact to keep these concepts intuitive.